So our next presentation is by Mitchell O'Sullivan. So if you can come up, Mitchell. Mitchell's doing a Bachelor of Science in Physics, and this particular project is titled Visualising the Orbits of Small Solar System Bodies Using Data from the Desert Fireball Network. And this will be demonstrated on the cylinder display during the demonstration session, and it's just holding a still image of his visualisation there right at the moment. So,
alrighty, good afternoon everyone. I'm Mitchell, and the project I was working on over the summer was visualising small bodies in the solar system using the data set of the Desert Fireball Network. So for starters, who are the Desert Fireball Network, or rather what is it, and what is their data set? So the Desert Fireball Network is an array of cameras set up in the Australian desert, all aimed at the sky, and they're programmed to look for fireballs, which are streaks of light made by meteoroids as they make contact with the Earth's atmosphere. In these cameras, they are capable of encoding data in the images, which allows the DFN group to map out the path of the meteoroids. Once they have this path, they can do two things. They can integrate forwards in time and see where the meteoroid landed on Earth, or they can integrate backwards in time and they can determine what kind of orbit it had. And we're going to be focusing on the second part, which is determining what kind of orbits it had. So at this point I want to show you this video, which was made in 2017 by California Academy of Sciences. If I can find that mouse. Alright. So this video visualizes the DFN dataset as of 2017. As you can see, it's objectively speaking quite visually appealing, and it's also quite accurate. So all these bright lights here are the meteoroids, and you can see them all landing on Earth. And by definition, every meteoroid detected by the Desert Fireball Network has to land on Earth at some point. So this is sort of what we want to be replicating in this project. So we can get rid of that now. Okay, so that problem was, that video was visually appealing and it was also accurate, but the problem is that it's now 3 years old, a little bit out of date. And if the DFN wants to visualize their new findings, they would probably have to make another video, which would in 3 years' time again become out of date, and you see the problem. So the solution that they came up with was, we instead make a 3D interactive dynamic environment that shows all the meteoroids detected by the Desert Fireball Network, and it will allow the DFN group to make their own videos, hopefully, from their own perspective by interacting with the environment. A really good side effect of having this environment would be to use it as an outreach tool to the general public. They can get an intuitive feel for what it is that the DFN are detecting. So how we go about making this project? The first, is this the pointer? Yes, it is. The first 2 points here are preliminaries, decisions that I had to make before the project started. The next 4 points are part of the project, things I had to do to make the environment. And the last one here is making sure that the data that I was showing was actually correct. So, first step was choosing software. There were 3 main contenders for this, and I won't go into these two in too much detail, but Unity was the one that I chose. And the reasons I chose it was because it could be exported to a lot of platforms. So you can do it on the normal desktop. You can also use your phone, and you can make web-based versions as well as Xbox and PlayStation if you really want to, but that's not really for this. It can also be easily integrated into the Hive screens. Maybe a year ago or so, one of the Hive employees made a tool that you can import into Unity that would automatically configure the camera to be used on the cylinder or the dome or whatever screen you want to use it on. So that was really straightforward and easy to do. Unity is also designed for both professionals and people just starting out, which is really helpful for me because I only had 10 weeks to do this and I had to learn it quite quickly. And also, Unity is commonplace among the Hive staff. So if I needed any help was right here, and I could get one-on-one contact with them, which was really, really valuable. The Unreal Engine is pretty much Unity, except it can render things in better picture. So it's more photorealistic than Unity. However, this requires more processing power and it's better suited for consoles like the Xbox or the PlayStation. And also you can't integrate it easily with the Hive screens. So Unreal Engine was out. The person that came, or rather the software that came second place was Sky. This is not a game developing software, but it's a platform specifically designed for astronomy visualization. And it's very easy to use. You can simply type in, I want to load up Venus, and then it will plot Venus for you. And you can also import your own data, so the meteoroids that the DFN detected, I could do that as well. However, the reason I didn't choose it was because it's only executable on desktops. There's no web-based version, there's no iPhone version, and in the future, if we want to make those versions, then Unity would have been the better option. And also, like Unreal, there was no easy integration with the Hive screens. So Unity was chosen because it was easily integratable with Hive screens, and also advice was readily available by Hive staff. All right, the second decision I had to make was choosing what Hive screen to use. I'm only going to describe the one that I chose because it would take too long to go through everything. But I chose the cylinder because, one, it can provide an immersive experience for a group of people at once, which is a really big advantage compared to, say, a VR headset, which can only do that for one person, or the Dome, same thing, just one person at a time. Also, its 3D capability partnered with its ability to fill your peripherals, while it gives you that immersive experience, it's also quite accurate in terms of scale. So in Unity, if you made things 1 meter apart, or in my case, 1 astronomical unit apart, then it would actually appear in 3D to be 1 meter apart in real time. So that was really good for a sense of scale. All right, so on with the project. I skipped a slide. There it is. The first step in the project was plotting objects in the solar system. I was given the orbital elements of every object, which is to say, every object that orbits something has 6 orbital elements that can describe that object's ellipse that it carries out. So you can convert those 6 orbital elements, which describe the ellipse, into exact XYZ Cartesian coordinates at a given point in time via the methods described in this really helpful book here. I did a way too big circle for that, but that book is really helpful, and it's well established since like 1998. So once we got the XYZ coordinates of all the planets and meteoroids, we were able to plot positions. And this is what it looks like. So you can see every white dot there is a meteoroid, and you can sort of see the little planets over there. Obviously, it's not to scale. If it was to scale, you wouldn't even be able to see the planets. And also, to clarify, even though the meteoroids are white dots in this simulation, in real life, the meteoroids would not give off any light, so you wouldn't be able to see them at all. But for the visualization, they're white, so you can see them. All right. The next step in making the environment was adding orbit lines, so you can better see where they are. The first one was solid orbit lines, so just to map out the entire ellipse that it was in. And the second one was fade lines. And I made fade lines because if everything, meteoroids included, had solid orbit lines, then it gets very messy, and you'll see that in action in just a second. So this is what the program looks like using fade lines, which is also on the cylinder up there at the moment. And this is what it looks like with solid lines. And as you can see, it's just like a crazy bird's nest of stuff going on. So that's why we have the fade lines. All right, second to last step was allowing access to the visualization. Now when I say access, I mean things like moving the viewpoint around and also moving through time, selecting points in time. So in terms of moving through space, I gave the user control over rotating the camera around a central pivot point, which the default was the sun. You can also change the center at which the camera pivots around. So for example, Earth, if you want to see at any angle, if you want to see a meteoroid hit Earth from any angle, then you can pivot around Earth instead. And then lastly, you can also zoom in and out of the visualization of the environment. In terms of moving through time, and this was a little bit harder to implement, there's three things. You have a time slider, which allows you to slide from the year 2000 to 2020, and that just sort of fast forwards everything. You can also input a specific date, which is really helpful if you know the date that a meteoroid hit Earth and you want to skip straight towards that and watch it in real time. And lastly, this speed slider. It just changes the rate at which days elapse in the simulation. And it looks pretty funny when it goes really fast, so that was cool. Lastly, these are the nice to haves, the extra functionalities. So first of all, in this settings panel, it was really designed for making the videos. It's for customizability. For example, you can turn the planets on and off, or even the meteoroids if you want to do that. Probs won't, but you can do that. You can also change what the lines look like, so you can change between solid and fade lines, and you can also turn them off completely. And then you can change the size of the planets and the meteoroids and the sun all independently. The second nice to have was this information panel, which appears when you right click on any object in the scene. And it shows you information. This information is all taken from the DFN data set. So the date of detection, the number of cameras that recorded it, and then lastly the orbital elements down there. This actually came in really helpful for me when I was trying to debug it. I could see what the orbital elements were of that specific object. It's quite helpful. All right, and after the project was made, there was a number of sanity checks that I did. I think there was about 4 or 3, but I'm just going to show you this one because this is the one that showed up bad results. And then it will lead into future work afterwards. So the sanity check here, it's the simplest one out of them all. If it hits Earth, then it's correct, because by definition, any meteoroid detected by DFN has to hit Earth. And some of them weren't. So this is a picture of all of the meteoroids' final resting places, according to the environment. The purple ones are the ones that landed in the right spot, so they all land on Earth's orbit line, and the red ones are the ones that didn't. And as you can see, they vary from close to just completely not right. So I plotted a bunch of their elements, orbital elements, as well as the other data in the DFN data set. But orbital elements was the most helpful. I plotted their orbital elements for the good meteoroids and the bad meteoroids. The bad ones are in red, good ones are in blue. This is the best case I found. It's got eccentricity on the y-axis and semi-major axis on the x. Briefly, semi-major axis governs how big the orbit of a meteoroid is. If it has a large semi-major axis, it gets really far away from the sun and then comes back in. Eccentricity, a large eccentricity means that the orbit is stretched, it's really thin, and a small one means it's more of a circle. So you can see that the bad meteoroids have generally a very large orbit because of the large semi-major axis, and a very large eccentricity, which means it's very stretched. And the fact that it's a gradual change from good meteoroids to bad meteoroids might suggest that it's an accuracy problem. So in the future, we might want to look into increasing the accuracy of the simulation and seeing if that helps. So we'll segue into future work, where the first point is further investigate this problem with the meteoroids. So that's the first thing you'd want to do if you wanted to continue the project. The second thing you'd want to do, I didn't actually mention this when I was supposed to, but when you plot the positions of all the meteoroids, some of them weren't plotted because they have parabolic orbits instead of elliptical orbits, and they're calculated slightly differently from the elliptical orbits. It's not difficult to implement, but it was just because we wanted to get it done fast. I just wanted to do elliptical for starters. So that'll be the second thing you'd want to do for feature work. Also, the ability to color meteoroids based on their groups or based on their elements would be very helpful for visualizing and for creating videos. And fourthly, something that I found would be very useful is having a search bar to search for the meteoroid you want. Because there's about 1,400 meteoroids in the data set all whizzing around the Earth, whizzing around the sun, it's really difficult to find the one you want in the visualization. So having a search bar and then maybe a flash of light when it finds it would be very helpful. And lastly, the coolest one would be putting it onto the hologram table. This also wouldn't be too difficult to do, I've been told. Maybe would take like 3 days to do. But essentially taking this static 3D model of the bird's nest, which is what I'm calling it, and then put it onto the hologram table so you can move it around and get an intuitive feel for it. Some things that aren't on here actually that I also wanted to put in was perhaps make a website version. So it could, this could have the potential of going onto the DFN website, although I'll have to, get permission first. And then also making an app, so a phone app or an iPad app. Those are the future things we can do with it. All right, so in conclusion, the impact that we're hoping it'll have, first of all, is it can be used as a tool for outreach, give the general public an intuitive feel of what the DFN are detecting and what the solar system looks like out there. It also gives the DFN scientists a tool for creating their own videos for presentation purposes and images for papers if they want to use it for that. Also, when it reaches a good level of accuracy, they can use this, the DFN group can use this to analyze their own results when they first come in and perhaps validate them that way. All right, and just wanted to thank my supervisors and the people at Hive. Special thanks to Patrick and Carly who helped me out a lot with the orbital mechanics side of stuff.